All right, guys. So we're gonna, for today's session, we're gonna cover off a couple of things. We'll look into some basic math notation, so you guys know, when I write things out, what those things mean, and I'll explain in pretty high level detail, not so much kind of into the fundamental principles of simple differentiation, so very basic calculus. I'll try and kind of find some links for you guys on other videos that will give you much more detail around the whole calculus space, and then we'll go through some of the math I think you're all probably missing for the linear regression. So for those of you who are at the actual kind of at the live session, hopefully what I'll try and do is answer the questions that you asked during our session in this real quick run through. Shouldn't take more than 15 minutes, so let's crack on with it. So we're going to start off with some relatively basic math notation, and I'm gonna use this today really in some of the stuff that I'm going to write out. So I'll kind of show you this notation. You've probably all seen this. Let me rewrite that. You've probably all seen the sum notation. Right, and that basically, if we have sum of x of I for I equals, let's say 1 to 10. Well, what that actually is obviously, x1 plus x2 plus dot 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 plus x10, right? So this is a simple way of writing this entire thing out, and in some scenarios, I'm going to just, because I don't want to write all this out, I might abbreviate that to something that looks probably a little bit more like something like this, where I go, well, for all I, contained within my superset of I, do the sum. And what this means is really, so there's a couple of things here which probably, if you haven't seen before, so if I explain that. So what this means, this symbol, the upside down capital A, is an abbreviation for just saying, for all values, right? And that's what that stands for. And it's obviously, so it's easy to write. And then this kind of epsilon, that just means contained in, right? So, and what this is saying is everything inside of I. So if we imagine like this, our I, our big vector of values contains, goes 1, 2, 3, all the way up to 10. Well, what we're saying with this statement down here is we're saying that, I is actually in part of, could be any one of these values, right? So that's what we're saying here. So I'll use this notation to kind of just simplify writing this out so that it's written in a more succinct way. And that's really, you'll see that come up quite often. There's one other thing that I'd like to kind of also show you guys, which you might not see, and it's usually done in the concept of a proof. And if I've shared any documents with you, you've probably seen this kind of backwards, capital E, and that basically means, there exists, right? Or it could mean, as and like hence or such that, right? So, for example, if I say that x will equal y in this kind of in some function of x, well then there exists a value of x, I in the large set of x, such that, so again, here's another notation, I suppose, it's just abbreviation of such that x, that's some value of x is equal to that some value of y, right? So it's a just simple notation. I just wanted to kind of raise this to make sure you guys have seen this notation before. It can kind of creep on you if you've not seen that before. So anyway, so wanted to kind of show you these couple of things. I will be using this notation for most of the way that I express sums, so just to keep that in mind. The other thing that I wanted to really briefly touch with you guys on is another simplification of notation. So you guys probably all have seen, the average or the mean is equal to, all the number of samples we have. So 1 over the number of samples for all I and I x of I, right? So you've probably seen this, and that's just saying, we're going to calculate the average. Another way of writing this statement is actually just to say this is x bar. So, so that I don't have to write all this out. And, if I have more than one average that I'm trying to calculate, writing it with the variable with the bar on top is simpler, right? It just reduces the amount of notation and simplifies that notation. So we're gonna, again, we will see this as well, and that will be quite an important part. If you've seen your lecture notes, you would have seen that in your previous sessions. So here's some notation that we'll use, some simple math notation that we will be using. So so it's probably kind of good to start off. So we'll go into looking at some simple differential equations. So some simple differentiation. So what's that look like? Well, okay. So let's go down here. Okay. So well, what's differentiation? Well, differentiation is actually, it's relatively simple. So if I draw this graph, you guys have probably all seen this graph before. So I've got y up here, x down here, and there's my graph, right? So we all know the function of this graph. If we generalize it, we have this function y equals mx plus c, where we know this value here, what m is our gradient, right? And what c is, well, that's the intercept. So you guys have probably all seen this before. Now, if we look at this case here, quite simply, well, actually, we know that here, when x is equal to 0, the intersect point here is actually 0. So we can rewrite this equation quite nicely to make our math a little bit easier into mx, right? So that's where we're at. So we've got this simplification, which is quite nice. Now, what differentiation tries to do is essentially saying, hey, look, I want to know for every change in x, how much of a change in y we're going to have, right? So every time I change 1 unit or half a unit in x, how much does that impact y? Another way of actually talking about that is actually the gradient, right? So what we're saying is for every one change, so the rate of change of y with respect to x. Now, you guys have probably seen these kind of notations. I mean, we all drive, the idea of miles per hour, right? So this is actually a gradient. So we're saying, well, okay, look, over a distance, your rate of change of that distance, the number of miles you're going to travel every hour, right, will give you your speed, right? So that's the vector. And again, there's that nice way of simplifying this, that concept. So the way to find this, as we kind of talk about, is to just say, well, Rm, if I just rub this out so we don't confuse things, Rm here is actually Ry divided by Rx, right? And that then gives us our rate of change, our differential, right? So basically our differentiation here is quite simple, quite straightforwardly done. So how do we go about doing that? So, okay, look, we're essentially trying to find what we would call a differentiation. So differentiation we write as d is the rate of change, the derivative of y over the rate of change, the derivative of x. So with respect to x, how much does y change? Well, in this case, if we do this, we know that that rate of change is m, right? Because of this guy here, we know the rate of change is m. Now, we can make it a little bit more complicated for ourselves, so we're going to do that right now. Let me just scroll down a wee bit. Let's have some more room. So let's make it a little bit more complicated. Let's say we've got this curve, right? So we've got a curve like this. So this is going to be, let's say, actually for the purpose of this, that's our differential. That's the functional form we have, right? Our functional form is y equals x squared. Okay, great. So how do we find the rate of change? So unlike on our previous example, where our rate of change was actually quite straightforward because we had a one-to-one in that sense, right? So we could calculate it here. We don't actually have that one-to-one anymore, right? We've got the squared value. It's it's not the same. Things will change depending, and of course we have this point here where actually there seems to be a very different change. We have a positive rate of change here, and we have a negative rate of change here. So obviously we're going down, we're going up. So this is a bit more complicated. Well, if we think about what we did here, we can kind of get back to it. What differentiation allows us to do is to say, okay, well, what's our rate of change of y with respect to x? Well, we can kind of go about doing this in a couple of ways. The simplest that I find is to go, okay, the way we're going to figure this out is, okay, let's look at this equation we've got. What's the power of x? And the power of x is 2. So we're going to bring that 2 down. And pop that 2 down here. And then we're going to subtract 1 from the power of x, right? And that leaves us with just the 1. So we've got our rate of change of y with respect to x is actually a function that looks at 2x. So what that is, if we draw this, is actually it looks like this, right? So now we've gone from this more complicated polynomial to a simple one-to-one relationship. And now we can kind of work out certain aspects depending on where we are on this curve, on this line. We've got this linear line, we've got this one-to-one relationship, and that then enables us to do things like say, hey, look, we want to know where, in this case, we've got this maxima, we know, we've got a point where things are getting really, really interesting, where nothing's changing. So we want to know when that's going to be 0, when in this linear way, we can do that quite nicely, right? So we can set this to say, it's 0. Now, we've seen this form of equation before, right? Wrote it out like this before. Well, in this scenario, our y is actually the dy by dx, right? And here we have c is actually 0, and our m is 2, right? So, hey, look, we've got this nice linear curve. So we're looking for this intercept point. We're going to go, well, when's that happening? Well, actually, when that's happening is when we've got this sudden change where it's 0. We can set it to 0. We can look for the intercept, and in this case, right, it's quite simple. It is actually 0. So we can do some cool stuff by doing this. Now, if we flip this curve on its head, you can notice actually instead of looking for the maximum point, we're looking for the minimum point, and you get different math here. So you get actually, to be honest, this curve here probably is more looks like that. So actually, what we are actually finding is the minimum. So it gives us potential. So this is where differentiation really comes in handy. It's quite powerful and quite useful. So at that point, we've covered off a couple of topics. We've looked at some math notation, some basic differentiation. Again, I'll try and find some videos for you guys to see more detail on it. We'll come on to linear regression and go through the derivation of some of that together in the next video. If you've got any comments, any questions, feel free to drop me a line, hit me up, and let me know whether you want something else covered. If you want to just put it in the comments, or whether you want to send me a direct link, IM me directly. All right, guys. See you later.